Okay, class. So in this video, we'll be discussing the main evidence you would need to answer our phenomenon for lesson 3 from unit 3 about the arrangement of atoms in compounds. And while we're covering those main ideas, you'll be completing kind of like this section of your notebook as guided notes, and we'll be discussing some of the main key points of evidence that you need. So we think our main question we're trying to say, why is sodium more stable than chlorine gas? So way over here on slide 63, we're going to try to answer that question, list the important evidence that could help explain why salt is less reactive than the two substances that form it, and give some reasoning, give some explanation about why. So starting here with this video, we can observe what happens. Let me see if this works in slideshow mode. Slideshow mode. Well, we'll just play it. How do you even... Oh, slideshow? Okay. Play from current slide. Okay, here we go. So this is sodium metal placed into the flask, reacting with the chlorine gas. We start to see big, bright flame, huge release of energy and heat, flame. And what you're left with would be just normal salt. So in that reaction, the first evidence we're going to consider is from our lab we did about the properties of compounds. We had citric acid, salt, and wax. The chemical breakdown of each citric acid was, so we had citric acid, its chemical breakdown, C6. Can I write with black pen? That would be good. Here we go. C pen. Blue pen. C6H H8O6. H8O6. Then we have salt, which is Na sodium chloride. And then we had the paraffin wax, which was some ratio of carbon and hydrogen, and what it is however many carbons there was, the number of carbons, what did you say, N, the ratio of hydrogen is twice that amount, 2N plus 2. And it's in a hydrous form, so we say it's also connected to, the citric acid's also connected. The wax is just like that. The citric acid is just connected to water, which may become important if we think of the properties here. So what was going on? What happened was the first thing to melt was the wax, melted first. This is the wax. This was the first thing to melt. And the citric acid started to melt. And then we ended the lab. Most groups decided this one was the last one to melt. So this can help us start thinking about why is sodium chloride more stable than sodium metals and gases. What we found out, our evidence here, our main piece of evidence from the lab was these forces holding this together are stronger. Because what happens when something melts? They separate into, their structures kind of liquidate. They can move freely. So in a sodium structure, sodium chloride, we have one right here. The forces between these formula units of each sodium metal and each chlorine ion, these two ions are very strong, much stronger than, let's say this molecule is right neighboring a different large molecule, and they kind of form these big molecule chains. So the wax is the first to melt, because this could actually be a big molecule chain. Let's say each molecule of wax is like seven carbons. And they're bonded. And they're bonded here. They're forming. And then there's also bonded to these hydrogens. Again, twice the amount of hydrogens. Plus these two on the ends. So something like that. So if you imagine, I don't know if I can copy paste this, but imagine this structure. Well, let's try. Let's see if I want to grab stuff. Oh, it just does that. Okay. Laser pointer. Ooh, laser pointer. That's cool. So imagine like the wax at the macro scale is huge clumps of these, and the salt at the macro scale is a nice geometrically crystalline arrangement. So our main evidence we discussed here about why this one melted is that the salt melts last because the forces holding them together are stronger. So this connection between the properties of the element and what's actually happening. So we can move into describing. So our one key, let's put that as one key piece of evidence here that that we got from our lab. Like one big, I want you to get like one key takeaway from each lesson here. So salt melted last. Oh, I should be not doing this for you. So I'm gonna add that to yours. And let me just make a copy of these slides so I can work. Make a copy of the selected slides. Okay. So yeah, salt. Did it copy all of them? I didn't see the last one. So anyway, add. So I'm going to be coming back. I don't think I got these last two. Let me get these into. Oh, there they are. I guess they just took a moment. Okay, so let's put one piece of evidence. Salt has stronger forces between its molecule, between its formula units holding them together. And that's why it melted. It melted last. That's a key piece of evidence. So then we talked about what are these bonds that appear. So another thing we discussed was electronegativities. So the difference in electronegativities determines how atoms will bond. So we could say the difference in electronegativities determines how atoms will bond. And what we're basically saying is, yeah, sure, close this. And what we're basically saying is, can I whiteboard? Let's just get rid of that. Cool, nice, cool, nice, nice. So have an atom with a valence electron, let's say sodium, and it has a valence electron in its outermost shell, like that. So sodium has one dot on its dot structure. Whoops, I drew too many. So cancel that, cancel that. So it has a pretty low electronegativity. So we said electronegativity is how strongly an atom can attract electrons from other atoms? Or how strongly can it? What's the force? The measurement of the force. It's like what force, with what force is an atom able to hold on to its own valence electrons? So if that force is very low, it's not holding on very strongly. And for an atom like chlorine, let's do chlorine. With almost a full octet of valence electrons, this has a higher electronegativity value. So we looked those up on our periodic table in our book. Wrong class. Let's see. Oh, I put it away, didn't I? Let me open this again. Okay. So, slide 43 has atomic radii. Okay, 46 has electronegativities. So if I find sodium, which is 0.9, and chlorine, which is 3.0, I can see chlorine is much higher than sodium. In fact, most of these ones way over here are higher. We talked about that in a previous lesson. So if sodium is 0.9 electronegativity, I'll just type it. Can I make my typing larger? Because that's incredibly tiny and not helpful to anyone. Type. So it's electronegativity for sodium is 0.9, and for chlorine, okay, for chlorine it's 3.0. The difference between those two, it is 2.1. So the difference is 2.1. And so if the difference is above 1.7, this will be called an ionic bond. Okay, so that's important to add to our summary slide about ionic bonds. Like they form when the difference in electronegativities is greater than 0.7. What actually happens is this single valence electron that, sorry if this is kind of confusing now, we don't need that really. This valence electron gets transferred over to the chlorine atom, giving chlorine a full octet of electrons when it bonds. So we can say now that chlorine has 8 electrons associated with it because of the one that sodium donated. It has a octet, meaning it has 8. So the octet rule applies, meaning atoms tend to be the most stable when they form a full valence shell with 8 electrons in that shell. As a trend, not a rule, there's certainly exceptions to that rule. But in general, most of them do that. So if it's an ionic bond, this is kind of strong here. If sodium bonds to sodium, that's a metallic bond. So we also said there are metallic bonds and covalent bonds. So covalent bonds would be when the difference is less than 0.7, and there were 2 different types. There were I noticed it's 1.7, not 0.7. So let's correct that. 1.7. So if it's less than 0.3, it's a non-polar covalent, which basically means like if electronegativity difference is less than 0.3, it's non-polar. And between 1.7 and 0.3 would be polar covalent, meaning like there's generally there's an electrostatic charge towards one side of the atom, or they're sharing these electrons. It's not a complete transfer. So when chlorine is chlorine gas, like we saw in the video, it's bonded, the formula is Cl2. And so 2 chlorine atoms bonded together, obviously the difference in electronegativities is 0. And they have a very strong attraction for each other, but they have a weak attraction to other chlorine molecules. So I would love to be able to copy paste stuff. I'll figure that out for the next video. What does this do? Cutout tool, shapes, bucket fill, hand tool. Yeah, I don't know how to do that. But so imagine cool. So imagine these. So now I have my hand. Okay, cool. Now, so this chlorine is a gas. It's moving around. It doesn't bond here. It actually just bounces off. So sodium, these ones lock in. The sodium chloride, this locks in to a shape where, it's going to lock in here because it has this characteristic where it's like kind of charged on one side more than the other. So sodium metal is just like a bunch of sodium metal, and the metallic bonds look like that. And the this is very reactive because of its low electronegativity, also, it explains a lot of its properties. Let's see, we have this video about, well, this is magnesium metal, but same thing. These electrons can just react with whatever until you, it's like, okay, right here, if you put an electric charge through the metal, we see it snaps the electrons into an arrangement. So now it can transfer energy through the metal.
Excuse this interruption. All the juniors going on these daily field trips, these reports to covered lunch area by 10 a.m. Okay, fine.
So our key piece of evidence here would be that covalent bonds have weaker attractions between molecules than ionic bonds. They have less difference in electronegativities as well. They share electrons between molecules, sometimes unevenly, resulting in polar covalent bonds. Some details there. So, key piece of evidence about that would be that the covalent bonds between chlorine atoms results in weaker attraction between those molecules. Of course, and then the sodium chloride is an ionic bond. That's another key piece of evidence there. And sodium metal is a metallic bond, and those atoms can move freely. The valence electrons, excuse me, those atoms as valence electrons can move freely throughout the substance, and that's helpful in understanding why it's so reactive with the chlorine gas. Lastly, in the next part, we predicted the structures of compounds in the formulas. So we can determine the ratio of different formulas based on what group it's in. So come back here and we'll just clear all these drawings out from here. So looking at our periodic table, and it's got hydrogen up here, and it's got helium over here. So sodium is in group 1, this group. And chlorine, these group 18s don't participate in any bonding, but chlorine's over here, and that's in group 17. So these group 1 elements all have one valence electron, and when they become ions. So like a neutral atom with equal amount